Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to engage with a little bit of I guess like Maxwell's equations, and hopefully through Maxwell's equations we'll probably get a better knowledge on I guess multivariable calculus, in addition to maybe a little bit of linear algebra as well. But you know, just basically just using our curiosity for physics to lead us into more enlightened connections with mathematics. Hey, Simplex, how's it going? Actually, I should probably give you a shout out. If you guys are not familiar with Simplex Pachinko, they are also an awesome math educational streamer. So be sure to give them a follow. They definitely know more stuff than me. So check out like any interesting puzzles they might try to solve, because I remember Simplex basically did some interesting mathematical problems that were pretty intriguing and probably way over my head, but you know, I'm not there yet, but hopefully I can get there. So alright, cool. Gave the proper shout out. Doing well. Maybe take a nap before stream later. Since I'm so nah, it's okay. Yeah, like my birthday's like the weekend coming up, so I'm gonna probably be like getting older too. So you know, gonna hit the 35. So like I usually like you're just about as old as you feel. So like for me, it's like I don't feel old, but at the same time I kind of like acknowledge the fact that people call me old, and I'll be like, yeah, you're right. I just laugh it off because it's like, you know, might as well acknowledge the fact that I'm an old man. And just get used to it and just like chuckle at it. Takes the stress out. And also guys, just a forewarning, just in case, if the stream just basically goes in and out sometimes, my internet connection is not the best, just to let you know. So if you notice that like basically the stream like slows down, or you know, like goes through like some weird hullabaloo, that's just basically my internet though. I don't think it's like connected to your guys' connection to me. But I am recording, so I will post the clear version on YouTube. So anyway, let's get into it, shall we? So I think we'll just look at the questions first. I do martial arts twice a week, and I'm going to get the kids out to bike as often as we can now they're out of school. Nice, that's good. Let's see, are there actual problems at the end of this chapter? Oh, there are. Okay, cool. I thought there weren't. Yeah, there's problems here. Are there problems here? Because we're doing the integral form and the differential form of Gauss's law. Okay, so basically the problems are way at the end. So let's take a look at what the problems ask. I guess that's how you basically read a textbook, right? You basically read the questions at the end first to see what you have to learn. To test the understanding of Gauss's law and the electric field, full solutions are available on the book's website, which we have right here. Find the electric flux through the surface of a sphere containing 15 protons and 10 electrons. Does the size of the sphere matter? Okay. Let's see, a cube with a size L contains a flat plane. There's a density. Okay. Okay, so these problems look interesting. What does this one say? Using the special Gaussian surface around an infinite line charged to find the electric field of the line charge distance. How many do we have? 15. What does the last one say? Find the charge density in the region for which the electric field and the spherical coordinates is given. Okay. So I guess we are having a slight idea of what we're looking for. I did read some of this before, like before stream, so I was like going through it a little bit. I think I had to read a little bit more on the surface integral. It's equals. So this one, individual segments. Okay, the area density and the area, the mass segment. So it equals mass. The closed surface, or at least the surface. So basically the integral with the surface. So my question is that when it's like a closed surface, like I know you write the circle in the integral sign. The one thing I'm wondering is, because like since this one doesn't have the circle, I'm like wondering if that makes actual difference, or is it just notation to show that it's a closed surface? How would you define a closed surface? The way I visualize it in my head is that when I see a closed surface, I think of like a weird shape, but it's like when you say it's a closed surface, I think like the outline of the shape is like completely like is basically like a dark outline. Like, you know how in cartoon characters you see a black outline around the character's shape. So I think of that. But when it's like not closed, I think of it as like, you know, like a dash line around the outline of the shape. Although like mathematically as well as physically, I don't know if there's a difference, or that's just the notation to basically say, hey, everything is contained within this surface. Integrals of mass calculations. Maybe that might be it. Let's expand this. Let's see the center of mass in one dimension. The density function, which represents a thinning rod or wire. Center of mass located at a point where the total moves. Surface integrals. It's L. Here we go. S. Here we go. Surface. Area, surface integrals. So, page 11. We're way past that. That's the one thing about like ebooks that you get online is that here it is, surface integrals. That looks... So it's all in... Oh, it's all in the vector calculus chapter. Do they cover, like, closed surface? In this? Here we go. Let's see, Stokes' theorem. Oh, okay. Stokes' theorem. The three-dimensional version of... Oh. So it's a double integral. Fascinating. So the Stokes' theorem is what leads us to make this into a differential form. Interesting. Hey, Fizzbuzz. I will give you a shout out as well. So if you guys are not familiar with FizzBuzz, they are another awesome math/physics Twitch streamer. If you like math and physics, be sure to check out their stuff. Spreading the curiosity and the knowledge. Alright. But how's it going, FizzBuzz? How's it going? What's the best part of your day so far, my friend? Probably should move this here. Let's see. Recall C is a closed, simple, smooth-oriented curve in the xy plane enclosed simply by the region R. I've always wanted to learn Stokes' theorem, but like, I don't know if I still have the mathematical prerequisites down for this one, because I do know what this is. I do know that's the curl of the field here. Now this double integral here. Going well. The best part of my day is talking to Slim and internet people about math. Nice. That's good. That's good. I think for me, whenever I read like books and then I see a connection with like a mathematical idea with something physical, I'm like, oh my god, this is something I've been looking for. Yeah, I'm trying not to bore you too much with like just basically looking over some like notes, well not notes, but mainly text from a textbook. I just want to see if there's any examples that I can do just to basically get my, I guess, my feet wet with this. But it's just so much text. I'm like, oh my goodness. Let me see if I can do some questions for my linear algebra course. I was starting to look at linear transforms, but there was one part, I think I was like looking, this one is about, oops, I forgot that. I have to, yeah, there we go. I wish they wouldn't make that the default. This should be the default, the thinnest one, but I guess some people just can't, I guess that might be just too thin for people to see, I guess. Maybe that's why they make it the default whenever you renew this. How was learning about Maxwell's equations going? It's fun to read about, because I thought that once I read like how, I guess, Maxwell equations like are set up mathematically, maybe I'll understand a little bit about the physics of like electromagnetism. But so far I'm only on Gauss's law. I didn't go over the other equations yet. I think I only went over the integral form of Gauss's law, but I'm still not finished with it yet. Okay, let's take a look. Okay, number one. Okay, so if vector A becomes B after undergoing the transformation, so now I guess we're gonna have to do, now the question is that, let's see, so this is 2 by 2, meaning that if we were to set it up as a vector, then it has to be because it looks like it's, because we can't have it as a row, I think, because it's supposed to be row and column, so it has to be this, because it has to have the same the number of columns has to be the same as the number of rows. If we were to, the integral form of Gauss's law is quite cool and deep. Yeah, I agree. I mean, hopefully when I get through, like, basically understand how you set it up mathematically and what problems it solves, maybe it will give me some more ideas on how, I guess, how the physical electric field works. So we do it like this, like so. I guess we can just do it like this, right? Or maybe we can just write it as, like, we're just multiplying them both. Which is vector B. So, bring it up like this. So if we have that means it's going to be 2. Yeah, because these will, like, kind of like go away, and we'll just, like, meaning that, so we have this row and this row, so minus, plus, just like that, and then this row with, yeah, this row with this column here. That goes like so, and that will result in negative 44 plus 2, and this would be 0 plus negative 12. Meaning that we're going to have negative 42 and negative 12. Okay. Let's see. Is that one of our answers? Yeah, that's one of our answers. And just checking my work, just so that I don't click an answer and then suddenly, like, it's wrong, and then it's like, oh, I forgot to check this. Okay. Yes, that's correct. Awesome. Okay, on to the next question. I was about to write polynomial, but it's not. No, it's polygon. are the vertices of the transformation of polygon given by -2? Maybe we should draw a picture just so that we can the first one is -2 to +1. Can we change colors? Yes, we can. So let's turn this into this. And for green, that'll be to -2. So right here, like that. And the last one, -3 to 1, which is right here. Okay. Now I think I saw like notes on this one. This one is basically a lot of it's very wordy, so what are the vertices of the transformation of the polygon given by... So I think like when they say polygon, like the shape it makes, I think like we have to think of it like this. So now I gotta think. So, like after its transformation, what are the vertices of the transformation? So, I'm thinking we have to transform all of these, right? By basically just using the linear transform of basically just using this to transform every one of these. I'm thinking that's what they're looking for, because we will get the endpoints of these in the new system, I think. So I think we'll try that. So I think we'll just call this one A. We'll just make it like, you know, letters. Even though it's math, there's no harm in trying stuff out, just to see if you're, like, I guess your logic is correct. Or at least my logic is right. But it's really interesting, because even though I'm familiar with linear transforms, I forgot that, well actually, I didn't even remember, because like I did take linear algebra before, and I knew about transformations, but I forgot about this picturesque way of actually looking at transformations. So I think what we need to do, I'll be right back, guys. Okay guys, I'm back. Sorry to keep you guys waiting. Anyway, let's get back to this. So, I think we have to transform every one of these by just multiplying these with this. So, I think that will probably not be an issue. So, I think we're going to call this A prime. So that way we don't get our letters mixed up. Hello, Super Brain. Nice name, by the way. I'm actually kind of envious I didn't think of that name. Super Brain. But what's the best part of your day so far, Super Brain? Yeah, that's gonna be 0, -2 plus 3. We're gonna left with 1, right? Yeah, -2, and then it'll be minus. Yeah, that would be a subtraction problem. So. Okay, so we got A prime, or yeah, A prime, which is 4, 1. Now let's do B prime. Then that is had some quite good food. Nice. What food did you have? Do you feel like sharing what delectable delights you had? So that would be negative. So it's -2. 1 plus 9. That's 10. Yeah, 1 plus 9. Okay. Let's just write this on the side here so that we can keep track of everything. So, okay. So next is C prime. Let's see what C prime is. So with C, we are given C prime. Oops. C prime is, and then that's 2. Had some tortellini with white sauce. Nothing fancy, but it was still good. Oh, that sounds good though. So I'm thinking tortellini, I think, is an Italian dish, right? Sounds delectable. Unless I'm thinking of the wrong food. Please correct me if I'm thinking of the wrong food. So right now I'm just basically doing some linear transformation problems. So nothing too difficult, because I was just reading a lot and I felt like maybe I should just do some problems, because if I read too much on stream, I'm like, oh man, I'm like, you get sleepy, and I'm like, no, I can't get sleepy on stream. That means I have to be doing problems now. So that's -4. And this is 2, -6 plus +2, that's -4, 2. Right? Yeah, so -6 I have my calculator with me, but I feel like the numbers are just too simple here that I have to like do it in my head. Like two, it's like that meme where it's like the engineering meme where it's like I need a calculator to calculate 2 plus 2, 2 plus 2. 2 plus -6, yeah, that's -4. -4 plus 0, it's -4. Okay, so this one is going to be -4, -4. Okay, now d prime. Lets me escape what Maxwell's equations are. Isn't that physics? Yes, it is physics. But also, I want to see the mathematical framework of Maxwell's equations. That's why I'm kind of like trying to get into it, because it's like, oh, it's allowing me to learn a little bit more of vector calculus, like without having to just go into just vector calculus. You get what I'm saying? It gives me like a physical intuition of how like vector calculus works, like in a physical sense. So that way I can have like good imagery in my head. That's usually how my brain works. -3, okay. Plus 0, 1, then 1 times -3 plus 3 times, oops, yeah. I think my 3's are very, very scrunched. And -1 to 3. Okay, so let's see, that will equal 6. So that's 6. And -3 plus -3, that's -6. Okay, so let's see if we have those answers. Let's see here. Okay, I think I see where ours is. I'm just making sure my numbers are correct. Okay, let's check. Yeah, we got it correct. Nice. Okay, last question for this section here. Number 3. What are the... Actually, before we get into the next section, because I feel like this is the time we can actually be a little bit visual here, which I think is going to be cool. So let's take a look at what this looks like. So I want to see how this transformation looks like, because usually the visuals in math are a little bit more appealing. So we are given, oh, we're going to have to draw more lines here. So let's do 6 on each end. So 1, 2, 3, 4, 5, 6. 1, 2, 3. It's not up to scale, but oh, maybe we should, so, because they're almost close. Oopsie. Yeah, it's almost close. So 1, 2, yeah, 2, 3, 4, 5, 6. Okay. All right, let's do the first one in pink. So it's 4 and 1. So 4 and 1, like that. The second one we'll do green. So this one's 2 and -2 to 10. Oh, this one goes all the way to 10. So I think we're gonna have to change this. So this one's going 1. So we had 6. I want to make sure I give like enough space here. Oops, I didn't mean to erase all of that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so green is -2 to 10. So it goes all the way up here. Oops. Let me just drag this down a little bit so I can actually see the... Oh, that's not great. I don't like the way it is, because the 2 is here, so I'm gonna draw the arrow here, and then like that. There we go. There we go. That's better. Now, next one is -4 and 4, so that would be right here, so there we go. We can erase like these blue marks here. And the last one is +6 to 6, so like this. Wow, that transformation really stretched it. So the way we look at this, so wow, look at this, guys. It's amazing how a transformation can change a space, or at least vectors in this case, or polygon. I was gonna say polynomial, but it's a polygon. That's pretty cool. Now I see why people really like linear algebra so much. It kind of makes you... The one thing I didn't know about transformations, which I thought was cool, was that you can transform a vector from one lower space to one higher space, and I thought that was pretty interesting. I haven't tried it yet, though. Okay, what are the vertices of transformations of the triangle with vertices that 3 was messy. Actually, it's funny because like transformations were like the thing that I couldn't get a full grasp on, like when I was like learning linear algebra, because it was just hard for me to actually remember it. But I think doing this with you guys has kind of probably helped me solidify my knowledge in it a little bit. Like I knew transformations were sort of like, I guess like the linear algebra way of writing a function, but I wasn't able to find do a mental, I guess a mental filing technique in my head to like give it a more solid foundation. So I feel like I'm kind of starting to see the appeal of linear transformations, and I have you guys to thank for that. Because my journey wouldn't be complete without you guys. The determinant of your transformation is bigger than 1, so it is expected that the polygon grows. Okay. That's something I probably will keep in mind. Thank you, Superbrain, for that enlightening, I don't want to say comment, but enlightening, it's something that's not a hint, but something that's very, now I'm like losing words. But thank you for that. Thank you for that. Okay, so let's do the same thing again. We're just gonna write these as vectors. So a super brain insight. Yes, insight. Yes, thank you, thank you. That is the word I was definitely looking for. See, sometimes I forget words too. Actually, I have a habit where like my friends are struggling with one word. Like if they're trying to say a certain word to give a certain meaning or a certain emphasis, I would basically start saying words out loud, and then they'll be like, "Yes, that's the word I'm looking for." Do you guys get that a lot? Okay, so now let's transform these things. A prime to... Oh, actually, let's make a visual, because it's a triangle. So let's make some visuals first, just to have more fun. So this one has... Okay, so we don't have to worry about it too much. Okay, there we go. Sorry about that, guys. Stream went offline for a bit. Don't worry, I'm recording the stream, so on YouTube I will upload the uninterrupted stream. That way we don't have to worry about the cuts in the middle. Yeah, my internet's not the best, so that's why I made a strategy of just basically streaming and recording all the stuff that I do on my streams, including my video game stream. So this one's 2, 1, 2. So we gotta go over here. So this is B. And the final part of our triangle is 1 to -2. So this one, we're gonna put blue. Like that. And that will be C. That'll be C. Then we will do a little bit of a... There we go. That looks pretty nice. No, it's not you, Super Brain. My internet's not the best, so sometimes stream does fail me sometimes. Okay, so now we can actually do the transformations. Here we go. Here we go. Here we go. So A prime, we're going to transform it like this. Actually, seeing the shapes makes it more appealing because it's like, oh, I can alter space like this just by having a matrix. So I can turn a shape into anything I want if I have the right parameters. So, like so, plus... definitely gonna get 0 on the top, so I think we're gonna have 0 and then -6. Okay, next up we're gonna have B, and that's gonna be transformed this way. Plus -1 times 2. Okay, 2 plus, and then okay, that results and -2. Yeah, -2 and 4. Okay. So now last one is C. And C, we're gonna have -2. So then plus -1 times -2, and then the next one is going to be times 1, and that's going to be times -2, which leaves us with +2, and that leaves us with 0. Okay, so let's take a look at the image, because I think that's another fun part we can do. So that's going to be -6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yep, that's 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and we don't have any higher numbers than that, so I think we can like start. So for A prime, I should say. Actually, I should put primes here. Oops. Prime and prime. There we go. All right. So for A, it is. So this is A prime, and then for B prime, it is -2 to 4. So 4 is right here. So B prime, and then for C prime, we have 2, 0. So it's like right here, C prime. Okay, now it's a triangle, so we're gonna do it like this. That looks pretty cool. And compare that to our original triangle. Wow. It's so amazing like how like these transformations just basically just kind of morph the shape. But I think that's pretty cool. Don't you guys? Alright, so let's see. Do we have our answers in this listing here? Yeah, I think I see it. So check. Yes, it's correct. Cool. Okay, we're slowly getting the gist of linear transformation, so that's good. So what's the next part of linear transformations that we have to go over? Oh, so now we're in kernels. So we're gonna do yeah, it's white. Okay, so pre-image, image, and the kernel. Hopefully I'm saying that right. Okay, so what I learned about the pre-image is basically like, you know how we had like the first vertices before we transformed them? So basically those are like the vectors we have before we do the transformation, and image is what we do after the transformation. So right now I'm going to be reading over notes, and I'll be summarizing what I learned here. So I'm basically compiling all the stuff that I read, so that way it just becomes a better way for my brain to like reconnect with it. Because sometimes I have a bad habit of just rewriting notes rewriting like information from like the actual book, and I just copy it, and that doesn't really like benefit me. So I just have to learn how to sit with the knowledge that I read and just like kind of filter it, so it's like a way that my brain can interpret it and get to the path much quicker. That's like I just learned that strategy like basically just now, like literally like at this age of 34. If I known to do that like when I was like early in school, I probably would have like learned a lot more than I probably would have. Okay, the transformation of the subspace. Finding the pre-image from an image. Okay, here we go. So now we gotta figure out how to actually get the pre-image, like the vectors we use to transform based on the image. So I think what we can write here is image to pre-image. So I think one example problem they have here is basically they give us the transform of how they get to B, but we just don't know what the subset A is, because we're trying to figure out what A1 is, which is the pre-image. So according to what they said, in order for us to like solve for like solve it, we have to do the inverse of so we're gonna have to, so we have to do the inverse version of this one with B in this case. So now I'm trying to remember, like without reading further ahead in the notes, how to get the inverse of something, and I think the inverse of a matrix, I mean. So I think the way to do that is I could be wrong, but I think the way to do that is by multiplying it by the identity matrix, isn't it? No, I don't think so. Because if you multiply it by the identity matrix, I think you ended up with the same thing. Like the same matrix as you had before. Let's see what they have in the notes here. Oh, so I think you have to solve it like a system of equations here. So yeah, because the way it looks like they're trying to solve it like it's a system of equations. Okay, so I think we'll write that as a note here. Use the original transformation and set it up with the unknown vector equaling actually I should write it like this and set it up as a product with the unknown vector equaling one of the vectors, or actually all of them. It might be all of them because I see both of them here. All the vectors in the image subset. I mean, that's how I can visualize it. Like, maybe the words are not exactly what it should be, like indefinitely, but it does sound like something like that makes sense to me. And I think they left us a definition of kernel, so we'll probably just write that down. Kernel transformation. Okay. And maybe we should write like a little math script here, just to make it a little bit more solidified. They used R2, but like I think Rn would also suffice. Okay. Let's see if we can take the pre-image and image quiz here. It's just 3 questions, but at the same time, it's something to get our feet wet. Okay. So now, number 1. Find the preimage of A1 under the transformation. T R2 Sorry if you hear chewing, guys. Like I have a cough drop in my mouth. I always take cough drops whenever I'm streaming, just to rest the throat, because I know I talk a lot whenever I'm streaming. Okay, so according to this, you have to set it up like so. So it's like, because the thing is that we're trying to get, so we'll set it up like this. And what we need to do is set it up so that we get the identity matrix on one side. So let's see if I can remember how to do this. So I think what we need to do is just basically, for row 2, we have to divide row 2 by 3. So leaves us just 1, and then we have like that. Okay. Now we can go on to the next part, which is, actually I should put dots here so not to get confused. Okay, so for row 1, we have to do row 1 plus row 2. Yeah, I think that's the right way to write it, because these two would go to 1, and this one, and this would add together to create 0, and this row, so 2 over 3, and 1 minus, leave us with 3 over 3, leave us with 1/3. Okay. Okay, so that results in, that's like one of the vectors in the set. Now I think we have to do the other one, so Let's erase this. Okay, so now we gotta do the other one, which is -1, 3. And what was the other one in the set? That was 3 and 5, so 3 and 5. So now we do the same things. So the first one we did was divide by 3. So this one's going to be, yep, like that. And then we did row 1 equals row 1 plus row 2. So yeah, these two cancel out, giving us a 0, and this one would be 3 plus which means we're gonna have to do this, which results in 14 over 3. So 14 over 3, like so. Okay, so A, or at least A1, I should say, has 1/3, negative 2/3, and 14/3 over and 5/3. Do we have any of those answers in here? I want to double check the last one just in case, because then that would become 1, and then basically 1 minus 1. And alright, so let's pick this and check. Correct. Nice. Okay. Getting the hang of it. We're slowly getting the hang of it here. Okay. Let's go down here. I always write the question down because there are a lot of times when I would do a lot of math and I would forget the original question, and then suddenly like, oops, I didn't answer the original question. Has that ever happened to you guys? Let's see, find the preimage of A and subset B. Okay, so I think we're doing the same thing we did last time. So now, row 1, we're going to do row 1 divided by -2. So this will be +1, 0, and then next row, we're going to have to do row 2 is equal to row 1 minus, actually row 2 minus row 1. So then this will be 0. This one will be 4. Okay, so now we're going to have to do this more on the other side. So we just have to divide by 4 in this point. So okay, so divided by 4. Oops. Let's turn it to okay, that's the first one. Now for the second one. So the first thing we did was divide by -2. This will be -1. And then for the bottom, you have to do that would be 0. This will be 4. So that's 3. Next we divide by 4. Okay, so according to what we got, -3/8, and negative. Oops. Okay, nice. We got that one correct too. Okay, third question. Find the pre-image of... So basically it's the same thing. So, okay, so this is good because it allows us to exercise our mental muscles for this. So that way we don't have to struggle so much for the last time, like for going over this material again. let's get to this. So, let's see, 5, -2. So we don't have to change the first part, the first entry. So now what we need to do is so I think we got to do the second row. So row. So that way we can get the 0 underneath. And then 4. That would be 6. And then for this one, 5. -2 minus 5. That would be -7. And afterwards, divide that by 6 gives us 1, and then 5, -7 over 6. Then we do the same cycle, so like 1 minus. So now we're gonna have to write, I'm gonna write it so that way we can have a better idea. So it will be row 1 minus 2 times, well, actually 2 plus, because this is negative here. -7 over 6. -2. That would be just like so. And now 5 minus 5 plus 2 times -6. That would be 7/3 and 5, 15. Leaving us with 8/3. Okay, that's one of them. Okay. Next one is -3/3. -3 and 1, so -3, -1, or -3 and 1, I should say. Okay. Yeah, it's probably better for me to like write these out so I remember what to do the last time. Luckily I wrote them down. So basically it's 4 plus 6, and then that's 4. Yeah, because like -3, so right. Okay. So now we have to divide by 6. Giving us 1 here. And if it's so it's 2/3. And then the last part, there's 1 here. So 0, and now we have 3 plus 2, giving us 4/3, -9 over 3, -5 over 3, 5/3, so A prime is the vectors 7, 6, and -5/3 and 2/3. Okay. Let's see here. Do we have that in our list? Yes, we got it correct. Nice. Okay, so far, so good. So we're pretty much doing pretty well in linear algebra. Let's see what's next. Linear transformations as matrix products. I think we'll probably leave that for like tomorrow's stream. So I think we're going to go back to Maxwell equations. Look it over a bit. Let's see what we got here. Oh, we kind of skipped ahead a little bit. So oh, this is really fascinating. Okay, so let's see, Gauss's law for an electric field. So you use the divergence theorem to basically transform it into the differential version of itself. Interesting. You use the divergence theorem for the magnetic fields. Okay. In Faraday's law, use Stokes' theorem, and then use Stokes' theorem for the Ampere-Maxwell law. I wonder why you used them like that. Because this one's just for the magnetic fields, and this one's for the electric fields. Faraday's law and Ampere's law, I feel like there's some similarity with, not the laws, but like the way they behave. They might have a similar behavior, that's why they require Stokes' theorem to transform them. I just wonder why though. Maybe we'll explain it here. Let's see the divergence theorem. The calculus is a vector calculus relation that equates the flux of a vector field to the volume integral of a field's divergence. The relationship between line surface and volume integrals works supported by some texts you will find the divergence theorem referred to as Gauss's theorem. Okay. Let's see, the divergence theorem states the flux of a vector field through a closed surface S is equal to the integral of the divergence of the field over a volume for which S is a boundary. Okay, so flux of a vector field through a closed surface is equal to, okay, so let's take a look here. So this is a closed surface. Integral of volume. Okay. This theorem applies to vector fields that are smooth in the sense of being continuous and having continuous derivatives. Okay. To understand the physical basis of the divergence theorem, recall that the divergence at any point is defined as the flux through a small surface surrounding that point divided by the volume enclosed by that surface as it shrinks to 0. A small surface surrounding that point divided by the volume enclosed by the. Let's see, the boundary surface, the flux throughout the faces of the boundary, positive flux from an interior cell is negative flux for an adjacent cell with shared face. Cell is identical. Okay, so I guess this is the relationship with the divergence theorem. So this is defined by the electric field is defined by the charge enclosed and the space of permutation of space. Charge density. The thing that comes to my mind is like, because they talk about charge density here, and I'm like wondering how to actually like think about this in this case. Well, I think here's like the answer to the question I was asking about why do we use the divergence theorem and the Stokes theorem here. Let's see. Stokes theorem. Whereas the divergence theorem is related to surface integrals to a volume integral, Stokes theorem relates to a line integral to a surface integral. Huh. Okay. Refers to this relation. You may encounter generalized statements of Stokes' theorem, but the form relevant to Maxwell's equations sometimes is called Galvin-Stokes theorem. Let's see. The circulation of a vector field over a closed path C is equal to the integral of a normal component of the curl of that field over a surface S for which C is the boundary. interior squares. Maxwell's equations to wave equation. For Stokes' theorem, it relates to a line integral to a surface. So this is a closed surface. Oh no, this is a closed surface. So what does the C represent? Oh, it's a boundary. Okay. So C is a boundary here. Because like right now I'm like visualizing like since the Stokes theorem revolves around like I guess like the bound, like it says the boundary, like the C is the boundary, so I'm thinking of I guess an electrical current that's like going around like the rim of like some sort of manifold or something, but it's not in the inside, it's literally like on the on its rim, on the rim of the manifold. That's like what I'm envisioning here. But let's see, the integral surface. Because since this is the curl, I'm thinking like it's sort of like no, I'm thinking of the gradient. Like I'm just basically trying to base it off math that I know. Gauss's law. I want to like actually like what it defines as first. So Gauss's law is a magnetic fields is similar in form but different in context from Gauss's law for electric fields. For both electric and magnetic fields, the integral form of Gauss's law involves the flux of the field over a closed surface. Differential form specifies the divergence of the field at the point. The key difference in the electric field and the magnetic field versions of Gauss's law arises because opposite electric charges, called positive and negative, may be isolated from one another, while the opposite magnetic poles, called north and south, may always occur in pairs. As you might expect, the apparent lack of isolated magnetic poles in nature has a profound impact on the behavior of magnetic flux and on the divergence of the magnetic field. should look what closed surface is first. Or closed surface integral. Closed interval, closed set. Right now I'm like just looking at like different resources for like understanding certain ideas. I don't know if you guys are familiar with Paul's online notes. I would use this like a lot. Surface area. Let's see, find the surface area of the part of the plane. It's a double integral with like a certain region. See that many examples in this one. Maybe I have to actually read through like the whole notes just to get a better clue, because sometimes like you're like whenever you like study, sometimes you like look over the notes and like it's just a lot of text, but then like you're trying to look for like, you know, those like bullet points where it basically is like, oh, this is the thing to look at. So I think I have to like really like look at this. Because I know when you do double integrals, you have to solve the inside first and then basically solve the outside. I think you can do it either way though. But if anyone like knows a different way, like which method is better, or if they work the same way, let me know in the comments down below if you're watching this on YouTube. Here we go. What you should first, you should make sure you understand the main idea of Gauss's law of magnetic fields. The total magnetic flux passing through any closed surface is zero. So the total magnetic flux passing through any closed surface is zero. About Gauss's electric field law. Hey, what's up, Sascha? Just caught us while we were doing looking up like Maxwell's equations, or at least the definition of them. Like we only got like 3 more minutes, so what's going on, my friend? What's the best part of your day so far? passes law of electric. Yeah, my internet is still like not it's not doing so well, so yeah, there's gonna be a lot of buffering. But I'm recording this this session, so it will be uploaded on YouTube. We were doing a lot of linear algebra before. Let's see, electric charge produced in an electric field, and the flux of that field passes through any closed surface is proportional to the change. Okay, so maybe we have to keep in mind of these laws, so maybe I should just write these, or at least like copy them down. So Gauss's laws, the electric version. Magnetism. Here we go. Copy that. Total magnetic flux that passes through is 0. I think we'll put Faraday's law. Let's look for that one. Because that way we can have like the main definitions of this. Okay, here we go. But first you should make sure you understand the main idea of Faraday's law. Right. Let's copy that. Paste. Then then we have, here we go. Ampere. And Maxwell, right? Yeah. Maxwell laws. So that way we have them all in like before us, so we know what to focus on here. Okay, you should know the main idea. I'm glad he like the author put it in a way where it's like just easy to access. Okay, so now we have all 4 equations before us, or at least like the way what they're defining. So for the electric, for Gauss's electric fields law, it says an electric charge produces an electric field. Okay, the flux of that field passes through any closed surface is proportional to the total charge contained within that surface. Okay, for magnetism, the total flux passing through any closed surface is 0. So for Faraday's law, changing magnetic flux through a surface induce an I think that stands for an electromagnetic field in any boundary path of that surface, and a changing magnetic field induces a circulating electric field. Okay, and Ampere and Maxwell's law. An electric current or a changing electric flux through a surface produces a circulating magnetic field around any path that bounds that surface. Okay. All right. So I guess that's a good way to end stream with basically the definitions of each law that basically will let us know how the math is supposed to work at what is the behavior of every single equation. Okay. So thank you for joining me, guys. Apologies for everyone on Twitch. I don't know what's going on with my Twitch. What's going on with my internet connection. I don't know if it's OBS or my internet connection, because it's never been this bad. I don't know why it's so bad. Like, I might have to either have my modem looked at, or maybe it's OBS's latest update, because I updated OBS and it started behaving like this. Or it could be a combination of both, but who knows. But thank you for joining me today, guys. For all those on YouTube, if you like math or physics, consider dropping leaving a comment down below, hitting the like and subscribe button. If you want to continue following me on my mathematical journey. For all those on Twitch, drop a follow if you can. I will leave links to my YouTube channel in the chat, in addition to links to the Discord, and a link to my Uncle Talk's channel. At this rate, I probably might record stuff for mainly the YouTube channel, if this keeps happening. But yeah, thank you for joining me today, guys, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream or / video. So take care, guys. Bye-byes.